started. So my name is Goa. Very happy to come here to share my research. This is my recent work on learning from naturally occurring human feedback. I'll pause at several points throughout the talk to take questions, but feel free to ask questions at any time. So human feedback has been a very popular term in the past few years, especially due to most recent advances in RHF research. RHF research tells us learning from human feedback is very useful. Let's take a closer look at the human feedback setup in their paper. So ABCD here represents model outputs sample from the same model. A labeler or a annotator is hired to rank the outputs based on the quality. Then the pairwise comparison feedback is derived from this ranking. So we can see that a more accurate takeaway is learning from annotator-provided human comparison-based feedback is very useful. However, annotations are very expensive to collect, and comparison-based feedback rarely occurs in practice because very few applications will directly ask the user to rank model outputs. Let's take a look at what human feedback we have in practice. We have a model being deployed or an agent in deployment. From this point, I'll try to use the word agent to emphasize the interactive aspect of it. So an agent interacts with a user. The notion of user here is in contrast to the notion of annotators, because users are not paid to do a required task. Users interact with the agent typically for some purpose they truly care about. Users often interact with the agent by sending a query specifying what they want or the conversation they want to have. Then the agent can provide a response to the query. As we emphasize, this response is often a single response, not multiple responses at the same time. Then the user can provide feedback to such response. The feedback can occur in various forms. It can be very explicit, such as thumb up or thumb down to directly telling the agent whether response is good or bad. Or more often, the feedback can be very implicit, reflected by user behavior. For example, if the user rephrases a query, then it's very likely that the past response the user sees is not very satisfactory for the user. Let's dive into a specific application, which is writing assistant. So the use of AI writing assistant is very popular nowadays. I bet everyone has used ChatGPT to some extent. As users, we often find that we need to revise the agent response before we finally using it. For example, GPT models tend to generate very formal outputs. I often need to revise it to make it less formal because I rarely talk or write in such kind of formal way. So based on this observation, we can see that every natural use of the writing assistant agent yields a edit feedback for learning. Note that even if there's no edit, that's also a very informative feedback saying that the agent response is very satisfactory. So we can see such edit feedback reflects the user's authentic expectations and individual preference. This goes beyond the genetic writing task, which is to generate something grammatical and fluent. So given that we know user edits are very helpful, informative, and abundant, the question is, how can we learn from such form of user feedback? This is a question we try to explore in this recent work. This is based on my internship project at Microsoft Research last summer, done together with my co-first author, Alexei, and Eduardo, Paul, and Dipendra. The title of this paper is Aligning LLM Agents by Learning Latent Preference from User Edits. As indicated by the title, we want to infer latent user preference based on edit feedback so that the agent can generate satisfactory responses that align with the user's need. In this work, we also want to take account of users' efforts on making such edits because it's an important aspect of the interaction and user experience. So the key here is to do correct preference induction so that we can get satisfactory responses from the agent so that the user only need to make very few edits in order to use the output. Learning user preference is actually very challenging because preference itself is very complicated. It can cover multiple aspects, for example, the level of formality, writing style, or rhetoric, or some specific wording. and each aspect have many possibilities. Regardless to say, different users have different preference. Even for the same user, some preference can depend on the context and can even vary over time. So for example, when we write emails to our advisors or superiors, they're very likely to be different from the email we write to friends or colleagues. In terms of preference learning, feedback in the form of edits is very implicit because edits itself do not directly express the underlying preference. We need to infer it. Because of this implicity, feedback in the form of edits may lead to diverse interpretations, especially for very nuanced changes in semantics. To address this learning challenge, we make a few contributions in our work on user edits. In this talk, I'll go over the framework we propose to formulate the interaction process and learning problem, and the method we introduce that implements this framework for LLM agents to infer user preference. I'll go over some findings from our experiments and analysis as well. After those, I'll cover some of my other work on learning from feedback, such as learning from other types of feedback and a method paper on end-to-end optimization based on downstream feedback. Okay, I'll start with the framework. So in our learning framework, an agent interacts with the user for multiple rounds of interactions. At every round of interaction, it starts with the user providing a context XT to the LLM agent. So this specific example, this context is the user provides an article and asks the agent to summarize the article. The agent can generate a response YT given a context. In this example, the agent generates something about farming. The user can read the response YT and edits the response if unsatisfied. This results in a revision Y prime T. So the color coding here is only for presentation purpose. Y prime T in our framework is actually a plain piece of text. The revised version of YT, it can contain multiple number of edits. These three steps form a single round of interaction. And then in this framework, the user can interact with the agent for multiple rounds of interactions. And every round, the context will be different. In this case, will be different articles to summarize about. To introduce the notion of preference learning, we assume the user makes edits to the response according to a latent preference F star T. So the subscript T here means that this F star, the latent preference can change depending on the context or depend on the time. With this assumption, at step 2, the agent will first infer a preference FT based on history and the context, and then use this inferred preference FT to generate a response given a context. So now the question is, how can we tell the quality of the learned preference FT? We introduced the notion of cost for this. So we introduced a cost function, which measures the amount of efforts the user put into revising YT to make it into Y prime T. So the intuition here is a higher cost means more edits or more effort spent by the user, meaning the response YT is not very satisfactory. So that the preference FT used to generate the response YT is not very good as well. So higher cost means the quality of the preference FT is lower. The overall objective for the agent is to minimize cumulative cost over time. So this is a full picture of our learning framework. I can take questions for this.
So is the delta sub edit the edit distance?
Right. So the question is for the cost function T is delta edit, the edit distance. It can be edit distance. And you're right, we use edit distance in our projects. But we want to make it this notion in the framework a bit more general. It's about the effort the user spend. So it can be the number of edits. It also can be the time the user spent on, let's say, staring at the output, trying to make some edits. Yeah, it can be more arbitrary and general. But you're right, we use edit distance in our paper.
Okay. So like if somebody was to simply rephrase, like keep the content the same but restate it, that would incur like a very high cost.
So depending on the cost of function, if it's an edit distance cost, yes, because it'll be as substitution, right? Substitution the same as a substitute with a different word. We assume the user make edits rationally. For example, the user does not make edits arbitrarily saying, I just want to spend more time making it.
Okay.
Yes. But you're right, depending on the cost of function, the amount of efforts can be different, can be scaled, for example. Okay, thanks for the question. So we refer to our framework as Prelude, stands for Preference Learning from Users' Direct Edits. This framework formulates the interaction process and preference learning problem with the assumption that the user directly make edits to the agent response based on a latent preference. And the agent infers the user preference from the interaction history and uses to generate a response. We formulate it as a cost minimization problem so that we can account for the amount of effort spent by the user on making edits. So next, I'll go over the method we introduced for preference learning, which implements this framework. Our method works for agents that leverage LLM by prompting. This means that there's no fine-tuning of the internal parameters. Our method specifically learns a prompt policy that can infer a description of the user preference. This is what I mean by descriptive. It's a description of the user preference in natural language, which is English in our case. And then this description of the user preference can be used in the prompt to directly drive the response generation. Here's a simple example. An agent has access to a prompt template. In this example, the template is simple. Write for this user who prefers something. This something is what the agent needs to learn. This is what learned by our method. Here are some high-level intuitions on how our method works. When user makes edits, the agent will induce a description of the user preference based on those edits. The agent will manage a collection of preference history, and given a new context at every round of interaction, the agent will infer a descriptive preference based on retrieving similar context from history. The assumption here is that the user shows similar preference for similar context in the past. So let's go through some technical details of method, which is under the Prelude framework. So this is a framework we introduced earlier. Our method works at the step 2, the preference induction part. So when LLM agent infers the preference FT, the agent will first retrieve top K examples from history. This retrieval is based on a context representation of the given context, which is the function here, phi xt. So here specifically meant that it's a vector instead of the whole piece of text. Then based on those retrieved examples, the agent will aggregate induced preferences in those examples and then form a single coherent preference FT. This will be used to generate response YT. Then after user makes edits to the agent response, there are 2 possible cases. Either the user makes substantial edits. So CT here is greater than some kind of threshold value. In this case, the agent will generate a preference F tilde to explain the user edits, because this means this is a new information that we learned from the user edits. Another possibility is that the user doesn't make any edits. CT could be 0 or could be a very small value. In this case, we can see that the response YT is very satisfactory. So the preference FT used to generate YT is very good. So we can use this preference FT as the preference F tilde that explains the user edits feedback. So throughout the interaction process, the agent will keep a history. This history is composed of context representation, which we're going to use it for retrieval, and F tilde T. Again, this is the preference that explains the user edits feedback. Yeah, question.
So given the context, how do you infer the preference?
So if we're starting from so the question is, given the context, how do we infer the preference? So if we start from very first round, then there's no history to infer. So the model will just generate something plainly based on 0 preference. And this will result in an edit feedback from the user. Then this is the second part. I see. So I can be very specific. So speaking of the summarization task, we'll go over later. So the prompt will be, this is a context, this is the article. Please summarize this article for this user. That'll be the very first prompt for the agent. And later,
you treat what the model generates after that as the preference, or
the model will generate a response, and the user will read the response and make some edits typically. And this edit feedback will be the one that we use to infer the preference.
Okay,
So for example, if the edit remove all the formal words, then the preference learned by the agent can be this user prefers casual style. And then this casual style and this context will be stored in the history. So next time, so for example, this is about say Reddit post, which is very casual. Later, when the model sees a similar context, say from Reddit, and then the agent will retrieve something from the history. Hopefully, we'll retrieve this example and then look at the inferred preference from the edits, which is like casual style. And then the agent will condition on this, say this user prefers casual style for this context, and let's produce a response for that.
okay, so I guess the thing that's confusing is in the loop, like,
Yep.
I don't see where YT prime or FT show up in like step 1 again. If that makes sense. So, like,
Step 1 again.
Like in step 3, there's this YT prime, like the revision, and then
Yes.
there's the latent preference FT that you infer, you guess. So where does that show up in the next round?
Ah, I see. So the Y prime T is not saved in the history. The F tilde is saved in the history. F tilde is the preference that explains the revision Y prime T.
Oh,
Does that make sense? We want to, so first it's a design decision. You can store Y prime T as well. You know, it's not bad to save more information. But in our framework, with our history only contains the context representation for retrieval and the F tilde T. This explains the user edits. So you can think about it as a one level abstraction to beyond the specific edits that we make.
so is F tilde T like natural text or?
Yes, it's in natural language. So out of the preference FT and F tilde T, they're in natural language. In our work, it's natural language. Again, you can make it more arbitrary. So, more questions? I can pause a little bit more.
Wait, sorry, I have one.
Yeah, sure.
How, in this step where you like try to look, you look at the difference between YT and YT prime, and then you try to get a preference from that, how do you prevent the FT that's generated by the model from just being something very pedantic, like, oh, this text differs in the third token, like.
Ah, I see. So this is actually specific to how you, so the question is, how do we know the quality of the F tilde T, right? Based on the pair YT and Y prime T. So this depends on the method. So I'll go over our experiments a little bit more, but in our experiments, we use GPT models. So it depends on the capability of the agent model. So the agent can infer informative or useful changes in terms of the edits. So that's kind of one of the assumptions about the method too. That's one of the reasons why we want to use pairs. Essentially, give the original summary and the revised summary. Because in that case, edits are different, so you can learn the meaning of the edits ideally. But if you just give the plain text, say Y prime T, this is a revised summary of the user, try to infer the preference, then that can be very generic. Yeah. So that's why we believe that when we generate the preference F tilde T, we actually use pairs to essentially filter out some like a trivial preference. Yeah.
So what's the assumed like scale of T here? Like how many previous rounds?
Ah, I see. So so in our experiments, we did 200 interactions. That means like research, you can think about 200 different articles for summarization, for example. Now this T, I think it can be arbitrary. Depends on, so for example, if you assume the user will have a small set of preference, perhaps you can learn that with a small number of T. But if you assume the user going to use it for a long time and the preference is more complicated, for example, not only changes based on the context, but also changes with the history, then this can be super big. Yeah, I think here I would say the size of the T depends on what kind of assumptions or hypothesis that we have about the user. Yeah.
What if the like some of the retrieved preferences are
so what if the retrieved preferences are contradictory to each other? So that's why here we have the top K examples. So in this aggregation process, at least that's what we see in our method, the retrieval doesn't have to be perfect. So for example, we use, I'll give spoiler alert, we use K equals to 5. So as long as say most of the examples are correct, that's what we see. And then the agent can actually, this aggregation process depends on how efficient it is. It can actually aggregate the useful ones, which are the ones that occur more frequently in those 5 examples.
The
Yeah.
aggregations also.
Yes, yeah, in our method, we use prompting for every single step. But again, it can be more elaborative in terms of having some learner model about it. Okay, thanks for the question. So we name our method as Cypher, or refer to it as Cypher. It stands for Consolidating Induced Preferences Based on Historical Edits with Retrieval. It's very computationally efficient because there are 4 LLM calls at max per interaction, and we only add a small increase in the prompt length. This prompt I refer to the prompt where we use to generate response. So the vanilla one will be, this is an article summarized for this user. And in our method, we learn a small sentence or a small description, short description about the user preference. So this only add a little bit in terms of prompt length. This method is computationally efficient in the sense that it requires very low memory storage. Recall that we save context representations, which is a vector instead of the context itself, which can be an arbitrarily long piece of text. Again, this is also a design decision. It's about how we're going to use the retrieval in our method. Cypher is also very user-friendly and interpretable. So users are not required to do heavy prompt engineering because the critical part of the prompt, which is the user preference, is learned by the model. Users are not required to express what they actually want. Users could read and understand the preference learned by the agent, which is in natural language, which is the part that we talk about in the QA part. And if you want to do something more complicated in terms of method, you can have human in the loop, like the user can even read and edit it. That's also an alternative way to do this. So I'll go over some of the highlights from our experiments. So in this talk, I'll go over one writing task, which is summarization. So the task for the agent is to summarize a given article. We use GPT-4 user as a simulation. So this user is to provide a context, which is to specify the writing task and provide some necessary documents. So for summarization, it'll be the writing task is to summarize this given article. The user can provide context documents from different sources, and it can have preference that depend on the specific context being provided. In this case, we're simulating it for different use cases. So let's look into this table to further understand what we meant by use cases. So we, based on the practical application of how people use summarization and writing assistant, we designed 5 common use cases, including introducing political news to kids. The source will be news article, or promoting a paper to get more attention based on paper abstracts, or taking notes for factual knowledge based on Wikipedia page, or use some online stories to get idea for creative writing. So Reddit post contains a lot of personal stories, or extracting main opinions from a movie review, where typically it has a lot of excessive details or sentiments and stuff. So we designed different latent user preference accordingly. So for example, when we want to introduce a news to kids, we better make it more storytelling, better in short sentences, a little bit more playful, more interactive, and more positive, etc. So we designed the latent preference based on each specific use case. Each one of our experiments has 200 interactions in total. This is the number I mentioned earlier, T equals 200. So note that at different run of interaction, the user is providing different contexts, essentially different articles summarized about, and the article could be from different sources. Implementation details of Cypher in our work including using GPT-4 as the base LLM, and the context representation for retrieval is MPNet. And we do top 5 retrieval with constant similarity. This means that we retrieve 5 most similar examples from the history. Our main evaluation metric is cumulative edit distance based on Levenshtein functions. So it measures the amount of removal, insertion, or substitution to turn one string into another string. So note that we're doing this over BPE tokens. Levenshtein functions are originally defined on character level. We also report the expense of using LLM, which is the total number of input and output BPE tokens. This is how OpenAI and in general language model providers charge their customers. So the numbers we report are averaged across the 3 rounds over different random seeds. We compare against many systems. In this talk, I'll go over a few of them. These 5 baseline methods are different in terms of whether they learn a interpretable descriptive user preference or not, and whether they use retrieval or not to use the history. The non-learning baseline is a vanilla baseline where the agent doesn't do any preference learning, just summarize the article using whatever default style the agent has. Continual learning baseline is to infer a preference using the most recent interactions. Essentially, regardless of the context, just look at the past interactions that we have and then infer a preference based on that. In context learning is to do this to retrieve similar context, similar examples from the history, and then use them as demonstration examples in the prompt. So the format will be, this is our original summary, this is a revised summary, and they're going to be k examples of those, and then ask the agent to generate a new response. Chain of thought baseline is a augmentation of the in-context learning baseline. So in addition to the retrieved examples, the prompt will specify that the agent need to infer a descriptive user preference based on those examples, and then use this inferred preference to generate a response accordingly. We also experiment with a Oracle method where we let the model use a true latent preference to generate response directly, because by design, we actually have access to all of the latent user preference. So this bar graph shows the result of cumulative edit distance. So lower is better. So we can see that Oracle method gets the lowest edit distance. Compared to other baselines, Cypher achieves the lowest edit distance. Recall that lower is better means fewer efforts the user make to the outputs. The green bars represent the expense of using LLM of each method. So we can see no learning baseline is one LLM call to summarize this given document. Oracle method add a little bit more expense on top of that because it includes the description of the user preference in that case. Excluding low learning baseline and Oracle method, we can see Cypher achieves the lowest expense. So we can see that Cypher is empirically effective with a very low expense compared to other baselines. Then we see Cypher achieves a very low cumulative cost. Now, we want to know whether Cypher achieves smaller cost over time. Recall this interaction is over time, multiple round of interactions. In other words, does the user make fewer edits to Cypher over time? Let's look into 2 possible cases of interaction outcome. One case is that the user doesn't make any edits to the output. So we call it a 0 edit example. So this plot shows the percentage of 0 edit example for Oracle method and Cypher. Cypher is in orange. So we can see that this percentage is gradually increasing, which is very promising. Another case is that the user does make edits to the output. We want to look into the edit distance to understand it better. There's a caveat of looking the edit distance directly because the response per each interaction is different in terms of the length. So instead we look at the edit distance normalized by the response length. This will be translated into the percentage of edits made to each response so that we can compare it in regards to the length. So the right plot shows this normalized edit distance. So we can see the orange line representing Cypher is decreasing over time, which is very good as well. So combining both graphs, we can see that the user does make fewer edits to Cypher over time, reflected by increasing number of 0 edit examples and decreasing percentage of edits to other examples. Yeah, question?
Why are they doing that 0 now? Like at the 0 round?
Oh, yeah, this is actually, this is actually binned across 20 rounds. So this is, you can think about this as the first 20 rounds.
Oh.
Yeah, because in order to show the trend, we need some kind of bin for that.
Oh, so, but like, where does it start then? Like, is it somewhere in between? Like, and then Oracle goes up and Cypher goes down? Like, it seems weird that there's such a giant gap within the first 20 rounds, and then it's like relatively flat for the rest of the.
I see. So the question is why there's such a gap? How do we interpret that? So let's first focus on the Oracle method. So recall Oracle method is generate this summary for this article given this latent user preference. This is the true latent preference we use in our simulation. So this black line is to show that regardless whether the model learns the perfect inference or preference or not, because we use simulation experiments, so we can still see some percentage edits. So the GPT-4 user will make some edits regardless, even if the generated response is reasonable.
Wait, so who's the user?
Oh, so it's GPT-4 user.
Oh, it's the GPT-4 model.
Yeah, exactly.
not like-
Not a person. Yeah, this is why I tried to explain earlier. We use GPT-4 as a simulation of the user. So ideally, we should work with human, but for analysis and then pilot studies, we actually use GPT-4 user.
But aren't you? Wait, I thought you were using GPT-4 to extract the FT.
Right, so there are two things. Yeah, I guess I see the confusion here. So the reason where exactly GPT-4 is used in this experiment. So we have two things. One is that we have our model, we have our method, our implementation of Cypher that it'll leverage LLM. This is GPT-4 in our case. We do this by prompting. And in our experiments, ideally, we should work with a human user to do this. But instead, we work with the GPT-4 user as simulation. So you can think about there are two components here. They just happen to be all GPT-4 models, but they don't have to be the same.
So how do you give, if it's not a real person, how do you make the GPT-4 model follow the link user preferences? Like,
Right, so this is what we designed this table for. So we actually use prompting to condition the model. So this is what, our paper has the exact prompt, but the prompt template is, the idea is that this is the this is the preference that you have, and try to make edits based on this preference, if it doesn't satisfy it.
is
yeah.
the model making the edits and the model judging the edits are the same. Does that cause some kind of bias?
We are trying to show that through this Oracle method analysis. This is what we're trying to show, because the Oracle method is that you're using the same model to judge it. You're using the same model trying to infer it. But to make it super clear, so the agent model does not know the latent preference the user model actually uses. Does that make sense? So they're not interacting in a white box way. So that's why I would say the best way to think about it that we just work with simulated user. We happen to use GPT-4 model, and then we double checked in our setup. It doesn't cause any caveats in our experimental results. Yeah, because there's no leakage about the latent user preference essentially. Yeah. Thanks for the question. Okay, so far the results focus on edit distance, which is a quantitative measure. Next, we want to look into the quality of the learned preference by Cypher. We conduct two types of evaluations for it. One is automatic analysis based on some similarity measures. This is not a very perfect evaluation, but does give us quick results. Another one is human evaluation, takes time, but more accurate. So for the automatic analysis, we make some assumptions. So recall that we have simulated user, and we design 5 latent preference for the user. So this analysis assumes access to all those 5 preferences. The question we try to answer is that among all 5 latent preference, is a preference learned by Cypher most similar to the correct one? So among all 5 of them, is the learned one most correctly to the one that is truly latent to this example? We compute the score using BERT score as a classification accuracy over all random interactions. So note that no learning baseline and in context SEL baseline, they are not interpretable in terms of they do not learn a description of the user preference. The Oracle method has access to the correct latent preference, so it's always 100% accurate. Compared to continual learning baseline and COT chain of thought baseline, you can see Cypher achieves much better accuracy, but still this accuracy is only around 50% in our analysis. So we can see that Cypher is better than baselines, but it has a lot of space for improvement. Yeah.
What is the classification?
Right, so you can think about we have 5 classes, which is the 5 latent preference we design. So every time we learn a preference, this preference is based on the user who have one of the latent preference, who shows one of the latent preference among the 5. So we want to compare the similarity of the learned preference to the correct latent user preference.
I see, but they're in both in natural language, so.
Yeah, so that's why we use the similarity measure. In our case, we use BERT score.
So it's a.
Yeah, so like more concretely is use a BERT score to compute the similarity between the learned preference with each one of the latent preference.
Oh,
And check which one has the highest similarity score. Ideally, it should be the correct latent preference for this example. So that's why I mean it's not a perfect evaluation because the similarity measures may not be that accurate, but it gives us some sense about the trend at least. Yeah. And then for a more accurate evaluation, we go for human evaluation. So we conduct the standard win rate evaluation with 7 human evaluators. So they need to give pairwise preference based on the output of Cypher and output of another method. So when Cypher goes against ICL in context learning baseline, Cypher's win rate is about 73%. When Cypher goes against the Oracle method wins. So Cypher only wins about like 24%. So this aligns with our experimental results. We also did another human evaluation where we asked human users to condition on the given preference and make edits accordingly to output of Cypher and Oracle method. This is the results averaged from 3 human evaluators. For cumulative edit distance, let's focus on the relative magnitude. We can see Cypher gets almost twice the amount of edits compared to Oracle method. So this gap is actually smaller compared to what we see in our simulation experiments, which is about 5 times more. We also report the percentage of 0 edit examples, which is 60% for Cypher and 77% for Oracle method. This gap is also smaller compared to what we see in our experiments. The gap was about 50% with our simulated user. So this human evaluation seems to suggest that the performance Cypher is indeed better than what we see in our simulation experiments when we go against human users. So to summarize a little bit, we study learning from human feedback in the form of user edits, which are very abundant and informative. We propose a prelude framework that formulates the interaction process and preference learning as a cost minimization problem so that we can take account for the efforts the user put into making edits. We propose a Cypher method that learns a prompt policy to infer a description of the user preference. This method is very computationally efficient and very user-friendly and interpretable. Our experiments show that Cypher is empirically effective with the low expense. We have more stuff in the paper, such as another task, which is on email writing, and more baselines and more variants of the implementation. We also have qualitative analysis and examples. For example, examples of the learner preference, example of the exact prompt template that we use. So please check it out if you're interested. So I want to give a shout out to our code base. So it's released on GitHub under the name Prelude. It's a modularized code base designed for easy customization. We have instructions on how to add your own task, specify your own user, and implement your own agent. Please check it out if interested. I can pause here to take more questions about this work before I move on.
You mentioned you have 20 minutes before
Yes.
Is it possible that in the middle, this actual is really close to your like original draft?
Yeah, that's a very good question. Yes, I would say yes. So we have examples of a sample to learn preference in the paper. I think I should be able to go there very quickly. So we do see some of the so let me make it big. Full screen. So these are some examples of the learned preference. So the left column is the correct latent user preference. The right column is the sampled preference. Essentially, we sample a different round. So you can see that around 100 steps, the learned preference is actually very similar to the latent user preference already. It captures some of the easy to learn keywords already. Some of the keywords are hard to learn. That's why the model is still struggling a little bit. We do not have very intuitive measures to directly show whether how steep the learning curve is for the learner preference itself, because we do show the plot of the cumulative edit distance, but that's an indirect measure of the quality. But yeah, I would recommend you can read this table a little more, and then we have our experimental results released in the paper.
So it is possible that in the middle it works pretty close.
Yeah, it could be.
And then
Yes, especially for example, if the retrieval part is confusing the model. Also in our setup, our user has a preference that changes based on the context. But another more complicated setup is that even for the same type of document, the user preference can change over time. In that case, that means that there is no specific stopping point for the model to saturate about. Yeah, but we didn't do these experiments, but I think our method actually covers this aspect because we do not make assumption about the stationary aspect of the preference. Right. I can take more questions or I'll go back to something. Okay, let's see. Okay, we're good on time, so I'll briefly mention some of my other work. So this work we go over is learning from direct edits on the agent response. I've also done some work on learning from simple categorical feedback. So this work, for this line of research, I mostly focus on question answering setup, where the categorical feedback is very natural and informative for that. So my work, let me start with the setup first. So the setup is a question answering setup with an interactive aspect. The user can ask an information seeking question and they get an answer from the agent, and then can provide user feedback. The option can be correct, partially correct, or wrong. So in our setup, we allow the user to choose one of the options. But more broadly speaking, in practice, you can derive such categorical feedback based on user behavior. For example, browse time or whether rephrases the query or not. In our work, we try to use this type of feedback to fine tune the agent and then redeploy it again to form a contextual bandit learning process. So my work covers both simulated feedback and real human user feedback based on crowdsourcing. Here are some highlights from the paper where we actually work with human users. So we cast a problem as a contextual bandit learning problem, and we introduce a fine-tuning method for categorical feedback. We show empirical improvement of the extractive QA system over time with human users. And we also did a lot of ablation and experiments to show that there is a lot of potential of domain adaptation in such interactive setup. We also do some ablation to show the critical part, the importance of the critical part in our method, which is to learn the answerability of the question first before we go for more fine tuning. So you're welcome to check the paper if you're interested in more details. So besides learning from different forms of feedback, I'm also working on developing better methods during training for practical applications of the agent. So let's be a little bit more specific about that. So far we've been talking about downstream applications. We have an agent or we have a model that will do something for a downstream task. But in practice, we often have a processing pipeline, and this pipeline often involves a retrieval. So the setup that the retrieval process will go for a lot of documents into several documents, and these documents will be input to the downstream model and do something. For example, for QA, it will generate output answer for it. So the path to work focuses on we look at the feedback of the output and then improve this downstream model. So what I've been doing this line of work is that, what about we take the whole thing, this whole downstream application as a feedback to the retrieval model so that we can improve the retrieval part as well, so that we can improve the entire retrieval pipeline. So a little bit more background about retrieval. So retrieval is to rank documents based on relevance to a given query so that it'll produce a ranking of some documents. Then those ranked documents are input to some downstream models, can be writing assistant, can be question answering system. This part is separate from training retrieval models. Conventional training objective for retrieval models is contrastive loss family. So this requires ground truth annotation for the relevant documents and some estimation for truly irrelevant document. People call it hard and negatives. So we can see that this is also not very natural in application. We won't ask the user to actually read all of the document and then annotate what you want is truly relevant. So to overcome this issue, we introduced a novel method, which is we call neuron PGRank, so that we can train retrieval models that can directly optimize the downstream utility. So this is what we mean by downstream utility. So utility function here is an abstract concept. We use the word utility to see how useful the ranked documents are to the downstream application. This is circled in this dashed lines. So it's a specific ranking, which is going to be input to a model for a downstream task, which we're going to produce final output. This whole thing will be the utility for this specific ranking. And then we use policy gradient method and this utility score to update the policy. The premise of this update is that we define the retriever as a loose ranking policy, so we can draw samples from it so that we can do end-to-end optimization. So specifically, we learn to rank by instantiating a LLM as a loose ranking policy, so we can do sampling. This enables end-to-end training of retrieval models as part of the larger pipeline by policy gradient based on the utility function in the end. So this utility function means that we can optimize the ranker for any loss function, evaluating the downstream performance, regardless of the specific types of the downstream model. It can be a white box, black box, or whatever architecture suitable for the task. And here we also we are also agnostic to the forms of feedback, because the utility function will be a single score out of the entire downstream performance. So this is ongoing work, but we do have a pilot study out, policy gradient training of language models for ranking, where we use NDCGI-10, a evaluation metric for ranking, as an approximation of the downstream utility. So in our paper, we show that we get very remarkable in-domain performance improvement. We also show a substantial out-of-domain generalization to some critical data sets, especially in EQA. This line of research is ongoing work for me, so I'm currently working on using the performance of downstream task as the utility function, which is more practical and aligns with the practice. So I'll end this talk with this overview of my work. I'm happy to take more questions or discuss more offline. Yeah. Let me see if I have questions online. Seems we're good.
Yeah.
Oh, thanks for that. Yeah, I can take more questions or. Yes.
So, have you thought about like learning from natural language feedback? So,
Yes.
from what you have residents, mostly like inherent kind of feedback, like the user edits or something.
Right. So the question is, what about natural language feedback? So first, I'll talk a little bit more about the motivation why I'm using these two forms of feedback. So I think natural language feedback actually need more efforts for the user, because you need to write and explain what you want. So I think for categorical feedback, it's very simple. You can derive based on the behavior, just one click. And for edits, I think edits are interesting in the sense that it's just part of the interaction process. The user will make edits anyway before using it. So the user only need to copy and paste to do that. That was the primary motivation why I started those two forms of feedback first. I think for natural language feedback, yes, I think it's more informative because the user will directly tell you exactly what they want, but I think also more efforts. Then there's a question about how many user or what percentage of the user will actually provide the natural language feedback for that. And how do we learn from this caveat a little bit, because the description of the language will be different. What I'm thinking, or I can give some the raw idea that I have on top of my mind. I think natural language feedback will be very useful if you actually want to learn a reward model out of it, because that's more specific. You don't need to actually compare in order to know which one is better or not, because natural language feedback will directly tell you what the user expects. So we don't need to do pairwise comparison. I think that can be integrated nicely into the utility function that we have, which also going to be a score for that. That's why I'm thinking that the processing pipeline, if we can optimize for the pipeline, then the natural language feedback can be a specific subset of the feedback, high quality feedback we want to optimize the entire pipeline. My best guess right now is that it's hard to expect all of the users to provide high quality natural language feedback, but we can think about task specific ways to learn from those feedback with assumption that only a small percent of user will make high quality feedback for that. Or more generally, go for the large scale setup, which is abstract away using some utility function, and it can be used into improve the entire process. Yeah. Question?
In this work where you're using the policy gradient to train models to rate, how big is the action space?
How big is the action space? That's a very good question. So, in our work, we did it for a second stage re-ranking. So the sample size is 1,000 documents
But
in
is
our,
it like,
in our training.
but is it like? Does it output a full ranking or?
Oh, that's a very good question. No, we do top, so let me see. In our training, we do top 20, NDCG at 20 as a score. But in our evaluation, we use NDCG at 10.
Okay,
So it's a design decision about like the top, how many top K documents you want to look into in order to generate the utility score.
yeah, because I guess like, yeah, the action space. is a bit too big.
Yeah,
It's
yeah,
like-
exactly. Yeah, so for our setup, I think it's common for retrievers. You actually optimize for second stage re-ranking. You use some kind of first stage retriever to get some number of documents. In our case, it's 1,000 documents per query already. And then you rank those documents. We rank this by doing sampling. I recommend to read our paper for detail. This is why we are introducing the Plaxis ranking policy. You can do sampling very easily for this combinatorial objects. Yeah, and that's if you're asking for information details, we use top 20 in our training. Essentially, we sample the ranking up to top 20 documents. Yeah, but for evaluation, we use NDCG at 10. I think that's more standard. But I also want to emphasize that in downstream application, typically is one document or top 3 documents at most, not even top 10. Question.
So this ranking, you're using NDCG as a utility function.
Right.
So, but like if I remember correctly, for like MS Marco, the way that people annotate the NDCG, like annotate the label is mainly like, does this contain the answer to my question?
Yes.
So I was wondering if you also thought about any of the utility functions, right?
Right. So yeah, here I actually have a backup slide for it. So to explain a little bit more. So utility function here. So recall that our pipeline is that this utility function tells us how useful this ranking is. So we assume higher utility score means this is more useful. Translating to that, if you have the relevant document in this ranking, then that is very useful. So NDCG score is an approximation of utility in our work, because this is another motivation we actually write in our abstract, that is evaluation of retrieval models is ranking, but training is pairwise. There is a mismatch in terms of that. So this utility function also brings bridges this gap for that. Specifically, in our pilot study, we see that does have a high correlation. So higher NDCG score essentially means you are getting better performance in the downstream applications. This is a pilot study. In our ongoing work, our utility function is actually the performance of downstream model. So if you look closely at it, there's a caveat about it because it depends on the performance of downstream model as well. So essentially, if the performance of the downstream model doesn't make sense, then you cannot even make good assumptions about the utility function.
So it seems like your utility is also dependent on the model, right? Like,
Exactly. Yeah, that's why the model is part of the utility too. So it's not only the task, but also the model. Because in practice, we do use a model to condition to use the ranking as input instead of having the human to write that.
yeah, I guess like for some models, NDCG at 10 might be a good approximation.
Yeah.
But for other models, maybe there is.
Exactly. So I think especially for prompt-based models. So some prompt-based models, I found it's interesting, is that the most relevant document, if it's closer to the end of the prompt, which is say if you're using top 3 document, if the relevant document is at the 3rd position, that gives you better performance because closer to the generation. That is counterintuitive towards ranking, because ranking the objective to rank it very high, right? So hopefully this abstraction of the utility function will account for that too. So whether you just hit the recall or you'd actually have the relevant documents ranked higher up. So I think that's a heuristic question, I would say, because it depends on the downstream model. Yeah. Yeah. Hello. Yes. Yes.
So basically, you know, like you're thinking about them using a contextual analysis.
Yes.
Yes, so you are like a multi-term.
Ah, I see. So in that case, we do not have past interactions. It actually directly optimizes. So let me be more clear about it. So this is how we collect the data. So this is what we meant by bandit. I'm showing that on the slides. So the human will ask an information seeking question and read the answer, validate the answer in the context paragraph and give option. So this is independent of all of the past interactions because every time it's a new question, it's a new context. So, yep. Sorry, what?
So basically, I was saying that even if it's emerging, all the Q&As are independent. What do you mean?
Yes, yes, but yeah, the learning part is to update the parameters of the agent. So essentially, it's trying to maximize the probability of the correct answer. So that's why it doesn't have an explicit component to retrieve historical examples. Yeah, because we kind of assume the reasonability is capturing the parameters, and that's why we only need to update the parameters without forcing some of the retrieval from history. Yeah.
There's no more questions, next question for Bob.
Yeah, thank you.